section I am going to explain what is additive manufacturing, then what is lattice structures. In next section I am going to share my research experience in last 6 years, how I utilize lattice structures to incorporate it on to the real world components like cross-sectional applications, like that things I am going to explain in the second session. So shall we start? Let's start. Okay. First of all, difference between the additive manufacturing with respect to conventional process. Actually, we have already well known about subtractive and formative additive manufacturing process, which is going to fabricate the components with the help of removing material or pouring material to the required shape. It will give more surface finished components, strengthened components compared to additive manufacturing. But why this additive manufacturing plays a major role? Why it is growing like this now? There is some point of things, especially benefits for additive manufacturing. First one is complexity. When you go with more complex structures and customized structures compared to other manufacturing method, additive manufacturing plays a major role. Then lead time. If you go with one or two components for prototyping and aerospace applications, you need only a few components at the rate of minimum time. So compared to conventional process, additive manufacturing gives a minimum lead time. Within 3 days or 4 days, we can get the optimized part or customized part. So because of these reasons, we need to learn additive manufacturing to shine in future. Then these are the classification of additive manufacturing. I hope you already learned previous sections. May I know what recent in which category we have these 7 categories. What are the points? There are 3 concepts. Why they have these 7 categories? First one is what kind of material we are using, whether it is a powder based or filament based or resin based. First point is this one, what form of material we going to use. Next one is how each layer getting fused or melted or sintering or curing. That is the second reason. Third reason is how the previous layer and next layer going to fuse together. This is the third reason. Based on these 3 reasons, we have 7 categories of additive manufacturing. In that, we are going to see about powder bed fusion process. Compared to all these 7 categories, powder bed fusion process is important to fabricate more complex and customized products. Why means we compared to resin or filament form, we have the material in the form of powder, which have more small in the shape. So we can get more surface finished components compared to wire-based additive manufacturing, that is called FDM. And other manufacturing processes like direct energy deposition and others. Okay. Then this is a powder-based additive manufacturing process. We have several categories in that. First one is selective laser sintering, which is more useful for polymer-based additive manufacturing process. Yesterday we showed you the machine side. That time I told you I show you the video. Now I show that one. So first you can see, then I will explain what is going here. Okay, you can't recognize more of this thing, but I will explain. First, what is happening is, this is the cross section which is going to sintered in the layer. See, first of all, this is the recoater which is wet the powder on the previous layer. Then little warm up happening. Then the laser which is not visible to us, it is sintering that portion here. You can notice now, you can see the black color cross section. It is sintering the powder. Then next layer getting spread over the part and get the layer get sintering. It will continue continue up to the completion of a component or how many components we starting here, it will continue. This is the process for SLS, which is selective laser sintering. Same process going to happen for metal additive manufacturing, which is called direct metal laser sintering. Both the video is taken from the machines of available in precision engineering technology, which is we saw in yesterday. Next video I am going to show you about metal 3D printing. You can visibly see the melting of the powder. The laser, here we using 400 watts laser. It is melting the powder. There is sintering nothing but the partial melting. Here full melting happening. So first of all, first layer get deposited on the build platform, then the layer get melted with the help of laser. This is the process flow for both powder bed fusion processes. So with these applications, what is the important of powder bed fusion process is nothing but the powder which is unsintered acts as a support for powder polymer based additive manufacturing, which is called SLS. In DMLS we need to give support structure. Even though we need to give support structure to fabricate more complex structures compared to SLA and FDM technologies, we can get more complex parts, which we shown already. So this is a laser powder bed fusion process. Then what are the things we saw in the previous slide is we know already. What is the additive manufacturing, what are the categories, how laser powder bed fusion is going to work, all the things we know, already learned. But in this session, what we going to learn is what is additive manufacturing, already know. But where we going to use, when we going to use, and how it will play a major role for new product development or any other product you need to enhance its properties. Also how it will helpful for the research. That things we going to learn. These are the 4 points we going to learn in this through this session. Then especially additive manufacturing giving freedom of design. Compared to other technologies, we can fabricate some of the complex parts to convention also. But when we highlight the additive manufacturing is with this category of freedom of design. It gives more and more freedom to the designers to design the parts with more complex shapes. Why? Because when we fabricate the part like topology optimized part, the other parts, it will more complex to fabricate with conventional process. For example, we taking one block of material and we need to remove the material from that. Now we need to do CNC coding for that. Then we need to select the tool for that. It is a hard for the tool to access the particular overhang and other cavity portions to remove the material. But in additive manufacturing, we going to deposit the material layer by layer only. So we can easily access the particular complex portion and easily fabricate it with the help of additive manufacturing. So this is the slide. We can see that when these 3 factors, first one is design complexity, then functional integration. Functional integration nothing but 2 or 3 components we have to part consolidate. Then it will give more functional efficiency. But when we reduce the parts, like I know part consolidation, I hope all of you know about part consolidation. If you know, I will explain what is part consolidation also. You can see 2 or 3 different kind of pens also, right? See, one is like kind of pencil type of pen. Another one is press type of pen. Compare both parts. One is have around 5 to 6 parts. One is only have 2 to 3 parts. See, this is the best example for part consolidation. Why? Because they think when number of parts get increases, it will get more fabrication time, material consumption, then assembly time, all the things is needed. But when we reduce the number of parts with the same application and same efficiency, we can get more cost effectiveness. For that, the part consolidation comes in the role. But when we use this part consolidation concept, the design of the part gets more complex. So that kind of things when it came, we need easy method to fabricate that one. That time additive manufacturing will helpful for that. Then third one is customization. Customization is it is in the area of the earth itself plays a major role. For customization is nothing but we each and every person here have customized their body, correct? No one has the similar kind of head hand or fingerprint, all the things. When we need of customization is, if for example one person get accident means they need to operate the broken hand and they need to put implant on the hand. With that implant, no doctor can't put already available implant. So why? Because the trap generated due to the accident is different from one person to other person, because it is not desirable one, already planned one. So in that kind of things we need customized implants, which is I showed here. So that kind of situation we need to fabricate customized product at the same time with minimum lead time, because we not let the patient to be with the broken hand for a long time. So that kind of portions when merged to these three merged together, there is a more innovative and more complex designs coming place. So that time additive manufacturing will play a role. This is the main advantage of additive manufacturing. So whenever we going to design a part for new product development, these are the basic four steps. First one is idea. When we go for any new product development, we think about what we going to incorporate in the product, what are the needed then the first step we get idea. It is a common thing where everyone can do. Then design. With we give the shape to our idea. That is the steps of design. Then in that steps we going to use SolidWorks, CAD, other 3D modeling and 2D modeling software. Then we give input that design to FEA step, finite element analysis. Then we change the if we satisfied with the FEA, we go for product development. Yes, but when it is a traditional process for fabricating any product. When we need to get more efficiency, more cost effectiveness and profit from our part, we need to add another one step is called as value addition. Okay, what is value addition? That is going to we see. This is the important step when currently in future generation and future also, we need to update ourselves to optimize our part to get stand alone in a market. Okay, currently aerospace applications and automobile applications are utilizing this value addition. For example, if anyone have a Royal Enfield bike here. Okay, fine. In a Royal Enfield bike, currently they are giving the name plate, which is which have the owner name in that, and they put that name plate in the petrol tanks. Side also and top of the petrol tank also. Also they in car companies, they nowadays they are providing the dashboard with the name of the customer. So it is a customized thing. So that kind of things will stand alone for the customer to attract the customer. That kind of things we have to add now. We need this value addition. So we need this particular value addition process. And we need to know how we have to apply that one to our product. That one going to we going to see about further slides. So these are the important value addition processes. First one is topology optimization. Second one is part consolidation. Third one is cellular structures. Actually, these three categories, these three are mainly used with additive manufacturing. Whether it is not only for additive manufacturing, that is not. It is already available. But when additive manufacturing comes play after 1980s, these three value addition processes techniques gets more visible to the designers, also industries. I will explain you step by step what are the things. First one is topology optimization. You can see the picture here. First product have the bracket, which is the bracket of automobile and aerospace application, which have full solid structure. When you going to use this one for the aerospace application, it will give more efficiency, but also give more weight to the airplane or other automobile parts. So what will happen? It will reduce the fuel efficiency. So what they done? They do topology optimization. The fourth diagram you can see that the optimized product. So it only have the material where the stress concentration going to happen. So with this they get more material reduction and strength also. This is the main concept of topology optimization. Next one is part consolidation, which is I already explained. To reduce the number of parts, with the same time we need to get more efficiency compared to previous product. Third one is what we are going to see, cellular structures. Cellular structures is nothing but the structures which have material needed where the stress concentration going to happen. I going to further slide we are going to see only about cellular structures only. So cellular structures is nothing but the interlinked networks of plates or studs. It have the more voids or open space in the structures. For example, you can see the windows here. It have the large side. That rods only going to withstand the load which is applied above the bricks of that windows. So like kind of structures will helpful for more efficiency. At the same time it will give additional application of to see outside people to airflow, also other application also it will give. So it is a simple object to explain what is the cellular structure. But in aerospace application we have many other structures also. We will see that one. Cellular, first of all you can see the top corner slide. It is the category of cellular structures. We have commonly two categories. One is sophisticated, another one is non-sophisticated, which is called as lattice structure. First one is foam, which have the unit cell, which have the population throughout its overall volume with random manner. Okay, it don't have the periodic manner. The unit cell populated with the random manner. There is no arranged thing. Then next one is lattice structure, which have the particular shape and also in x, y, z direction. It is populated with a particular dimension and distance. It is called lattice structure. In that also we have different categories. First one is 2D lattice structure, another one 3D lattice structure. In 2D lattice structure we have only studs or faces in the only two directions, x and y. In 3D we have unit cell which is populated in x, y, z in 3 directions also. Why the cellular structure is more efficient in the study means because of these applications only. It will give for application for biomedical applications, then heat transfer, vibration damping, aqueous insulation and energy absorption. Okay. Then lattice structure. We in cellular structure we have particularly we are going to see about lattice structure. Why means it has the designed shape. So we can easily design with lattice structure. We can also do tailored application. We get tailored application. That means appropriated needed application we can easily get with lattice structure. Why should we go for thing is it will give more high strength to weight ratio. If I have more solid one cube, I am giving the load on it, it will give more. It will absorb more energy, but it has more weight also. Compared to that, if I go with cubic structure with have the stud in that and more voids in that. If I give load on that, it will absorb the energy also. At the same time, it give minimum weight to the component. So, is the main reason. Then it give more thermal damping and other applications. In industries, compared to other applications, 30% of application, 30% of usage for lattice structure is energy absorption. For glass worthiness and for you can nowadays they avoid car bumper, right, which is outside of the car. But inside there is a bumper which is useful for absorb the energy during the accident, and it will resist the impact load to the passenger and other engine parts. So there is a beam and a glass box which is going to directly absorb the impact load. So that two things currently there is a needed research also going for incorporating lattice structure to particular structures. So that is it. Now we are going to see about other slide, a methodology, how we are going to incorporate this lattice structure to the particular components. You can see what is this one? Can you recognize what is the component that one? It's a turbine plate. Turbine plate. Yeah, it is a common turbine plate. But what we done is we incorporated lattice structure to that part to get weight reduction and energy. Weight reduction and efficiency to get. So I am going to tell what is the methodology we need to do for incorporating this lattice structure to a common part or mechanical part. That is called latticing. Okay. First of all, these are the steps. First one is concept and objectives. Then selection of unit cell. Then design space, population and validation. These are the steps we have, and many things we need to consider during this latticing. Okay. Why I am particularly taking this topic is currently during my research time also we tried many projects and tried to publish on that one, but many times it get rejected. Why? Because here we are doing the research which is new to us with the equipment available for us, but when we submit the paper, it is going to around the world. Anywhere the examiner there they will examine that paper and tell it is already available research. But how they are telling is they have equipped researchers and equipped machines in the lab and countries. So we need to understand what is the current market. Then only we can compete with the others and get our paper and our research to publish. So that kind of thing we need to learn this kind of new technology, part consultation, topology optimization. Even latticing also have many research papers in academic area. But still now it have more research gaps and areas. In future you study these things and do with your students also, it will be more helpful for students and you can get easily acceptance of research. First one is concept and objectives. What is that? Is nothing but if I am going to incorporate my lattice structures to a component means first of all I need to find what is my objective. Whether I am going to increase the energy absorption or I am going to reduce the mass or weight of the component, or whether my application is thermal side, or I need to going to reduce the vibration. Like this kind of objective, first of all I have to finalize in the first step. Next step, what is the mechanical target my thing? Whether where I am going to change that one. Whether the response of the test result. For example, all of you done your tensile testing, right? With the help of UTM. We done a tensile test with many people done a composite research, right? There they will do dark bone shape and do the tensile specimen test. There, sir? Yeah, we fabricate the tensile sample and then test with UTM, universal tensile machine test setup. In that we get stress strain curve. How we compare that stress strain curve means we only going to see about what is the strength, what is the Young's modulus, and compare previously available data. But here what we need to do is we have to change the response itself, not the value or not the what is the compression strength or energy absorption. That one not our aim. We have to change the response strain curve itself. Then only we can it will directly impact on our mechanical properties. That I will explain how it will happen. Then first one is selection of concept and objectives. Whether you have more clear on that, then we go for next one. That is called selection of unit cell. Actually, Based on the structure and deformation behavior, each and every unit cells classified under mainly two categories. First one is bending dominated, another one is stretch dominated structure. What is this called means? When the load going to act on the lattice structure, it will deform with two categories. One is bending of its struts or stretching of its struts. So based on that, Maxwell, who is the researcher, make two equations. One is for 2D structures, another one 3D structures. It is the image we can see. It is the 2D representation of lattice structure or unit cell, which will explain how the lattice structures have strut and node in that. Here, in the equation, S is called as struts, number of struts in that. N is called as node. That is the junction point of two struts. So, if you select any unit cell, based on that, you can you count that part, the number of struts and nodes. You apply this equation and get the value M, that is a Maxwell index, which is below 0 means it is a bending dominated structure. So, whenever it get compressed, it will bend, struts get bent and deform. So, it will give higher energy absorption with minimum stiffness. When M is equal to 0 or above 0, it will stretch dominated structure. So, it will absorb more load in elastic region. After that, it get deformed plastically and it will give minimum energy absorption. So, it will be more useful for strength, where is the strength needed. That places we can use this kind of structures, stretch dominated structures. So, commonly we have three kind of lattice unit cells. First one is stretch based, then next one is plate, another one is TPMS. TPMS is nothing but triply periodic minimal surfaces, which is more helpful for heat transfer applications and biomedical applications. If you are going to incorporate these kind of structures to your implant in medical application, it will give more surface area to grow your tissues and the implants. So it will be more helpful for biomedical applications. There is a software for generating these kind of structures. In that software, you can easily, by giving the value to the structure, you can easily fabricate this kind of TPMS. But when you go for this kind of sheet-based lattice structures, when I started my research 2015, I can't easily get these structures. So what I done is, each and every strut I fabricated and I assembled it, and then I fabricated as a lattice structure. But nowadays we have different softwares called entopology. Then SolidWorks library also have this kind of unit cells. And then Materials Magics have the softwares unit cell library. That kind of software easily we can get this kind of lattice structures. Particularly entopology giving 1 year of academic free license. You can utilize that software. Simply giving your ID card and mail ID, you can get 1 year of free full access software license. Then you can utilize that software to your research work. But when that is also founded by the research scholar who struggled more in his research work. So after his research, he found this entopology software, and now he giving 1 year of free license to the academic persons especially. So I told already, right, I am not going to see about the mechanical properties. I am going to change the response. This is the response. This is a sustain curve, which is nothing but the force displacement curve which we get from the tensile testing or compression testing. It is this diagram getting from compression test. I told already two kind of structures. One is bending dominated, another one is stretch dominated. Here, these bending dominated structures, when you give a load upon this, it will bend and absorb the energy with smooth region of this one. Actually, we have three regions of sustain curve. First one is elastic region, in which we remove the load, it will come back its original position. But when it comes into the plastic region, it get permanent deformation. But in comparison, we have different kind. We can see different kind of responses. This is called plateau region. Okay, if the structure is bending dominated, we can get this kind of smooth deformation, which will be more helpful for energy absorption applications. But when we use this kind of stretch dominated structures, it will resist the bending dominated movement, so it will stretch like this and deform. So what will happen? It have more compression strength, that means stiffness. Then after that it come down and deform as like wavingness, wavelengths will be there. So it will give more strength, even though it will give more stiffness and strength, it not give more energy absorption. So both structures will be best for both reasons. First one is for energy absorption, another one is for higher strength and stiffness. So whenever you are going to do research or do new product development, you are going to use lattice structure, means you have to finalize which structure you are going to see. Then based on that you need to select your unit cell, then you incorporate that unit cell to your structure. Then after if previous step is completed, means I selected my unit cell. Then what I am going to do? I am going to finalize where I am going to incorporate my lattice structure. That is called design space. In even topology optimization, other part consolidation also, we need to consider this design space and non-design space. Here, any load not going to happen or acted. So this portion where stress concentration will be more, that place I am select as a design space. Where directly the load going to act or any mating places, that place I am consider as a non-design space. So I take this design space, then I incorporate my lattice structure to the design space. Okay, these are first step of incorporation. First of all, in this step I selected my design space. Okay. Next, I finalize my stud configuration. If I go with a lattice stud based unit cell, means I can control my cross section of the stud and length of the stud, by which means important parameter is relative density. Relative density is nothing but the density of lattice structure which is compared to the solid structure. If I have this is my lattice unit cell, right? Yeah, I take two kind of components. One is this kind of unit cell, then full solid unit cell. By comparing this both density of components, I get small value, right? That is the relative density. The equation for that is the density of lattice structure to the density of solid structure which have the same dimension. It is called relative density. Okay. First of all, I have to fix my relative density. Based on that relative density, my cross section and length going to fix it. Another one thing is aspect ratio. Aspect ratio is nothing but L by D ratio. That is length of the stud and diameter of the stud. If we have to consider relative density also, the same time it should come as acceptable aspect ratio. Okay. Also we need to consider DFAM, design for additive manufacturing here. If you go with additive manufacturing with powder bed fusion process or any other technique, we have to consider what is the minimum feature that can be printable or fabricated by the additive manufacturing particular process. So, if I am going to take FDM technology, means the dimension should be minimum 1 mm. Or even SLS also we can go with 0.8 mm diameter also we can achievable. But doing the post processing, it can maybe get break. So we have to consider minimum 1 mm for SLS also. For DMLS we can go with 0.5, 0.6 mm diameter also. That things we have to consider in this section. Then cell size. Cell size is nothing but the size of the cube. Okay. This is a cube. The dimension x, y and z is the cell size. Commonly we use symmetry geometry only. That means cube shape of lattice structures, unit cell. So we have to think what is the size of the x, y, z of the unit cell. So This diagram you can see the voids, that is gap of the lattice structure getting reduced. Compared to A, B have minimum voids, C have more minimum voids. This is nothing but A is 10% of RD, that means relative density. B is 20%, C is 30%. The scientist who is named as Gibson and Asway, both persons, gave one book for this particular cellular structure. It is a cellular sonic books. Also they have uploaded the video which is taken in the Texas University for the students. It is available in YouTube also. In that you can search this all the information and you can get. In that they explain that above 30% of relative density, the structure acts as a solid structure with minimum force. That means above 30% of relative density, you fabricating your parts means it may act as a solid structure. So what happen is that time the application, the response from the when load is acting on the cube or any object, you incorporated 60 or 70% of relative density lattice structure to that object act as a solid structure. Okay, so the structural applications, structural property of lattice structure, you can't get to that 70 or 80% of relative density lattices. So you need to get more energy absorption and stiffness. You should use 10 to 20 or 30%, maximum 30 to 40% of relative density you should use. Above that, it will be act as a solid structure. So if relative density is 70%, structural property get demolished, material properties will be more. Okay. Then population technique. That means I finalize my unit cell dimension, all the things. Then how I populate to my design spaces. There is different techniques there. First one is gradient, functionally gradient structure. Okay. There is uniform distribution also. Then functionally grading. That means I will increase my relative density from portion by portion, by layer. This layer not consider for layer additive manufacturing layer thickness. It is some height we consider as a layer thickness. Okay, layer by layer we can increase our relative density also. If our components like of cylinder, we can give radiant grading also. Why this kind of things we will need means if my component going to get impact or minimum impact during the environment, means we need to have more hardness. So I will deposit my high strength of lattices to outer shell. In inner shell I will use minimum relative density or minimum strength of lattices. So it will give more material reduction and energy absorption, also cost reduction also. So these are the important applications of grading of lattices. Here we only incorporated single lattices with different volume, that means different densities. But we can also incorporate different units as a single object. You can see here, three different lattices, what they incorporate this one and they done the research. You can also do like this kind of research, but where the problem will come means the junction of the both relative units. It only plays a major role. We need to more concentrate on this one, and we can, if we achieve this one, we can get more applications and more properties that I will show you next slide. It is called IPL lattices, that means interpenetrated lattices. If I need to incorporate two lattices, first I will move on. This is interpenetrated lattices. It's nothing but we incorporated, for example here, we incorporated bending dominated and stretch dominated lattices. What will happen? We can achieve both properties in a single unit. Okay? It will give more energy absorption also. It will give more stiffness also. So you can see the graph here. The first one is giving more, what is it called, strength. Second one is minimum strength. When we combine both, we can get average stiffness, also higher energy absorption compared to both other unit cells. So this kind of technology also you can use. This is called interpenetrant lattices. So I stop with this. After taking break, we will continue.
Sir,
Do you have any doubt with the previous slides? Anything, na, please. Nothing, na, we can go further. If you need any suggestions, if you have to tell any suggestion like I am going fast or too slow or not understanding, please let me know. Based on that, I will change my percentage. Okay. Next thing, these are the unit cell, different unit cells, how we can utilize both properties in a single unit cell, like that studies we learned. After that, these are latticing strategies. Another one is we now we can understand how to populate our unit cells in lattice to the design space. But this is another one important thing we need to learn, how we going to fix that our lattices to that particular design space. There is two concepts. One is non-conformal, another one is conformal. What will happen now? In non-conformal, we take our cube of lattice unit, then we merge that to our design space. Then we do Boolean and remove that outer area of our lattices and design space. So we can get, it is fully based on the outer contour of our part. So what will happen? We can get some voids or gaps in that. So what will get? Unmerged area of studs or faces. So what will do in the environment studies or experiment, what will happen now? The trimmed area will get more stress accumulation on in that place. So it will impact on the mechanical properties. So compared to non-conformal, always we can use conformal thing. In conformal thing, what we going to do, based on the outer contour or outer edge of the component, design space, we will arrange our lattices based on that. We see here we have the outer horizontal line. That horizontal line, what we going to merge with that is with the contour. So our lattice in the direction of based on the curvature or shape of the design space. Okay. Here not like that. Here the lattices are in the direction. With that we will trim the lattices with based on our design space. But here we populate or pattern our unit cell based on the design space. So here when we giving the load, the distribution will be good compared to non-conformal strategy. So we can get more application compared to non-conformal in the conformal design stage. Okay. Then validation. Then up to that we need we completed our incorporation of latticing. That is latticing. We complete that latticing. Then what we need to do is, before going to fabrication, we need to do computation analysis. That means FEA. That thing compared to other, if I have complete solid structure, I am doing FEA now, that is different category. But when we go with this kind of complex structures now, that is different category, because in this we are going to get more issues compared to conventional designs. What are the things I will explain next slide. Before that, what are the steps we need to do? First one is we have to incorporate our files to here with step or IGS. Commonly I am speaking with the help of Abacus or ANSYS software. So I am considering that software, then I am formulate these steps. But first thing I need to incorporate my lattice structures to the component, to the software. Okay. Then I need to assign the material properties. How I can assign means, especially for powder based additive manufacturing, it is an anisotropic product we can get. That means in X, Y, Z direction we get different kind of properties compared to conventional process. Conventional process like casting or forging, now we can get like 90 to 95% of isotropic properties we can get. But in additive manufacturing, mainly we can get only anisotropic properties. So in the initial stage of research or anything, we need to fabricate tensile coupons, then we need to test that one, then from that test we need to come up with the Young's modulus, density value, other things we need to calculate. Then we need to give that as a material property to the our design. We can't directly take the available library material properties. It will not give the exact result. Okay. Then second step is assign material property. Third one is meshing the lattice structure. It is a more and more complex process. We know different kind of meshing there in Abacus or any other software like tetra meshing, cube meshing, like kind of different kind of meshing there in FEA. So which is suitable for us, we need to decide that one. For that also we need to do iteration steps. We need to do what kind of test now? I should take one cube of unit cell, like I think I am telling this single unit. This single unit I need to take in FEA. I give material property, then I give different one kind of mesh type. I need to do testing. Like kind of thing, iteration I need to do for different unit cells, different kind of mesh size. Then I finalize what mesh size will be good. First thing. Next, mesh size. First type, then size. What is the mesh size will be good. For that same procedure I have to do with different mesh size. That is called conversion test. I need to take all the result, then do one graph. In that graph I need to finalize, okay, this after this mesh size, the result not varied too much. So that particular mesh size I have to consider. For that initially I put higher mesh size. Step by step I reduce the mesh size. Then which mesh size my result are not get different too much, that mesh size I have to finalize in this step. So meshing is a very important step. In that also we have different software for that. One hypermesh is one kind of software to get precise meshing. Why? Because after getting my result, I need to compare with the experimental also. So at the same time I can't directly fabricate my part with additive manufacturing. Why? Because sometimes if product is small or based on the situation, material, method, the cost will be high with additive manufacturing. For that particular thing, I need to finalize my mesh designs all the things with the FEA and finalize thing. Then only I go for fabrication. So I finalize all the thing with meshing step. Then I go for boundary condition. Boundary condition is nothing but how the test going to happen, what are the load condition I have to do, where the component going to fix, all the things I have to do. For example, I am going to do compression test for this cube lattice structure. I have to fix bottom plate. Okay, bottom plate I have to fix. For that type constraint there. That one I have to give. Then top portion I have to give compression load. So here I have to fix x equal to 0, y equal to 0, z only the direction, how much distance it should compress. That thing I have to give. These the things I have to give as a boundary condition. Then next step is analysis step, which is nothing but what kind of analysis you going to do. Explicit, dynamic, static. There are different kind of types. In that, what kind of type is suitable for your lattice structures for your environment study. So that kind of analysis type you have to give, then run the simulation. If your RAM is minimum like 16 GB or 8 GB, your one simulation take 3 to 4 days. minimum 3 to 4 days. Then what happened? If completed, not an issue. In between power went also there is a issue. You have to start from the scratch. Otherwise, sometimes it get error and stop also. So we have to do with the more conscious with this analysis. In my research time, I tried for 3 years. At the end, I can't run my FEA. Why? Because I got only minimum RAM of system. So if you want to show your FEA, you need more configuration system. If you done that one and show in your paper, definitely your paper will get accepted compared to others. Because what happened, even me also, I done only experimental and submit my paper. It get first time rejection, second time only accepted. So in that also you need to give more new thing on that. So FEA, if you go with FEA, you need to get more configured system. If you done that one and publish your paper, it will get accepted quickly. Then post processing. Post processing is nothing but you completed your test. It came as completed. Then you have to get result from the analysis. Same as experimental. Experimental, what you going to get? Stress strain graph, right? Like that you can get from the FEA also. That FEA graph and test graph, you have to compare that both things and then your result and FEA get similarity. So your test and design strategies all are correct. You can justify with that one. Also, not only values, numerical values, you can also show your deformation behavior also with your result. So during your comparison test, you have to take a video of that one. Then you have to compare each and every layer how it deformed. Like that you have to compare also. Then validation. In that, what are the issue we facing? Already I told. First one is computation cost will be high. In outside, in center, you are going to approach and ask for the FEA analysis. They will charge 3,000 to 4,000 for 2 to 3 hours minimum. But your analysis is going to run for 3 to 4 days. Then cost will be more high. First one. Next one is meshing difficulties. If your structure, obviously we are going to 1 mm or maximum 2 mm of diameter of structures only. That too more complex structure. So meshing is more difficult. So you have to sit for that and do 1 month of meshing. Then only you can get proper meshing for your lattice structure. Then third one is contact and boundary condition challenges. Why? Because I have this kind of cross section. When I particularly give contact area for that, I have to select each and every top surface of the stud. Then I have to merge that one with the compression plate. So that time it will take more concentration work that needed. Then non-linear material properties. This is a behavior we can get with the compression test. Already I show you, right? Elastic region, then plastic region and densification region. 3 region we will get with the compression of lattice structure. That all are not linear one. Only elastic region is a linear deformation. Other things are non-linear. So to get appropriate result, you need to select non-linear behavior with your software also. Then only you can get. Then accuracy with this simplification. That means if you need more accurate result with the you need to compare with the experimental result, means you need to go with minimum size of mesh. It will take more time. Otherwise, I will only going to see the deformation only. That means you can go with maximum mesh size. So based on that, you have to get thing. But what happen now? If you go with the maximum size of mesh, sometimes error will happen. Then part FEA is interrupt. So these are the things we need to do. Then post processing complexity. Actually, when you get post processing, you need to get graph, right? The stress and strain value. You have to select a particular point, not full component stress and strain curve. You can't get. You should select only one point or one mesh. in that mesh you need to plot the graph. Otherwise you select all the point now. Yeah, I need result for overall component means what will happen is that it will give number of graphs. That means XY graph itself. If your component have thousands of elements, it will give thousands of graphs. But what is the truth is, your component having lakhs and lakhs, above lakhs and lakhs of mesh quantities. So what will happen? You will get lakhs and lakhs of graphs. You can't in your life, not even me also. In our life, we can't study that lakhs and lakhs of graphs. So what we need to do? We need only select only one element with this overall component. In that we need to take graph for that. So this is the important thing. But another one thing is node. Node is nothing but the junction of two sets. When we go for meshing that one, there will be a problem. Why? Because there is not specified shape for that. So there will be, if I go with meshing, there will be an overlap of meshes. So we need to think and we need to filter each and every mesh and do rework on that. Then only we can get proper results. Then final step is fabrication. If FEA all the things complete enough, we go for fabrication. What will happen is, if you go with conventional, you can do. Because nowadays additive manufacturing not visible for all the people. Here Chennai they can do, Coimbatore can do, Trichy people maybe do, other people can't do. So they will go for conventional process. But when they will go for conventional process, some of method I show. First one is coagulation method. What they done now, they take a sheet of paper, sheet of material. They with the gear profiles, they can get particular shape. Then they stack one by one. They can get different shapes. Okay, that is the first method. Next one is with the help of water jet cutting. They will cut the cross section. Then they will paste it and they can get. Like casting also we can do. But what is the complex? What is the drawback in that? You can't go with complex shapes. You can use fabricate only conventional traditional lattice structures, which is already available, like cube structures, kind of structures only we can access with the conventional process. So even though conventional process can manufacture lattices, but it is restricted to some of the shapes only. We can't get all the shapes. Why should I go with all the shapes, different shapes? Means I need to get different properties. Only cube property I get now, there is no use of lattice structures. I need to get different properties of that. So we need to go with different shapes for our product. That plays a major role for additive manufacturing. So in this place only, additive manufacturing plays a major role. Here I show you two different techniques which is powder based only. First one is laser powder bed fusion process, which is called as FDM, SLS also it comes place for this, or DMLS also. What going to happen is, the recoater loader going to deposit my material on the build platform. Then it will laser sinter and the cross section. Then it will go down, bed go down, then next layer. Like that, full fabrication process complete. Then we take it out and clean it. But what is the thing we have to consider during the fabrication is, we need to finalize the post-processing techniques. If we go with polymer-based post-processing, we need to focusedly clean the powder. Before that, we are during the finalize the step dimension also, we need to consider what additive manufacturing method we are going to do. Whether powder-based, we need to we need the provisional to clean the powder. If this kind of samples I am going to fabricate. I can see more of whites here, so I can easily remove the powder, unsintered powder here. But when this kind of density or dimension getting increased, the voids get closed. So what will happen? The removal of powder is more difficult, especially when I incorporate this part to this lattice structure to particular parts. Like this kind of parts I am going to incorporate now. I can easily remove the powder center of it, but in the corners I can't remove that one. So we have to plan for that, and based on that we need to design also, we need to finalize the dimension also. So based on what are the manufacturing method also we need to consider. So during this value addition process, that means even topology optimization, part consolidation, we need to plan previously for the first step to last step. We need to consider all the steps. So we, based on that, we finalize each and every step, and we have to do. For metal kind of fabrication process, we anyway for lattice structure we no need to view for support structure. So we can easily remove the powder. But what happen if you go with a cube kind of thing? Metal powders maybe stick on the surfaces of the studs. So we need to cautiously clean it. Then we have to do dimension verification, all the things. That time we can see some of the powder stick on them. We need to study that things also. How we can go with CD scan, micro CD scan we can do. We for justification purpose. That means whether I complete my research and fabrication, I tell I got these samples and this dimension, this relative density. The question will arise: how you tell you got this dimension? You design for 0.8 mm. Then how you justify you got with fabrication with 0.8 mm? That much question coming now. We have to do CT scan, micro CT scan for that one. Bad luck is we don't have micro CT scan here. Especially that is industry grade micro CT scan. Even industry have also they not allow us to take. Actually, during my research around COVID time, I done my research. I try for micro CT scan. No place is there. Then I go for CT scan. But what happened? That is COVID time. All people are checking for COVID. In fact, whether they get COVID or not. So that time I can't access that facility. Even I done that one also. After CT scan, I can get DICOM file. Okay, that is a file called DICOM file. We incorporate that file to Materials Magic software. That is Mimic software. Magic's Mimic software. That Mimic software study each and every layer. Even our body we take a CT scan also. It gives each and every layer. That every layer we have to top view, we have to check and finalize the diameter of the structure. Then we can tell this is the diameter. I come up with my CT scan, what I designed. So it both are with the acceptable deviation. So I get proper output like that. We have to justify. These are the process flow for design, fabrication and validation of lattice structure incorporation. That is. Okay. Any doubt in that, sir? This portion completed with this. Next thing I will share my research work. Any doubt in this, sir? Shall we go next one? Okay, sir. Hereafter, what I am showing, all the things are particularly around 70% are already published one. Other things are not published. If kind request, don't take any photograph. If you need journal paper references, I will share you. Here I am going to share what are the 6 years of work what me and my team and my guide Dr. Jeremy Kano, retired professor, with us and our team we completed these works. I am going to share with you. Any doubt in between you can ask. First thing, with the polymer additive manufacturing, SLS technology, I fabricated my lattice structures to study the how lasers process parameters impact on the property of lattices. That I got with the help of lattices I done this work. Actually, what is laser parameters? Actually, this I show the machine which we saw yesterday have 240 parameters inside. 240 parameters like laser parameter, beam offset, how material have to flow, then how laser move, that FT lens how it have to move. For each and every powder, it have own 240 parameters. Yeah. So this machine actually closed license machine. If we need, already we have in PETC we have PA1 material license. If we go with different material, we need to buy the material also and need to buy the license for that. License will cost of 10 to 15 lakhs. It simply come up with only one pen drive, only one folder, only one file, not folder also, only one file. But that is a cost of 10 lakhs. If in our company also we miss that one also, there will be a big trouble. So why I am telling me, what is the importance of this parameters only I am going to tell. Why? Because each and every parameter plays a major role on property of product. Not only lattice structure, other parameters also it will play a major role. So in my initial research work, it is a pilot study of mine. What I have done is, I just fabricated my Kelvin lattice structure. Kelvin lattice structure is nothing but which is can be easily seen from the bubbles, soap bubbles. We while washing the cloth now we can get bubbles, right? Like kind of bubbles. From that bubbles only Kelvin the researcher found this structure, and this structure comes under bending dominated category. Okay, there is no vertical studs. Here we can easily find out bending and structure dominated structures. How means if the structure have vertical studs, it will give structure dominated behavior. Vertical and horizontal studs means if you have with your structure with a bending inclined structure, it will obviously give bending dominated behavior. If you have merged both horizontal and vertical and inclined, the properties will get changed. Okay, I will explain that one also. So in that laser parameter, particularly there is 240 parameters. I take only laser parameters called laser power, laser speed, how fast it will move, then laser diameter, sorry, hatching distance. These three I take.
Actually, what is the hatching distance?
Yeah, I will explain, sir. I will explain. First one is, why I take these three parameters is, it will control the energy density of the laser. In particular layer, how much the volume of energy density should place on that sintering process. That is the main parameter or main thing we have to consider. Okay. In that, first of all, what is the laser power means? How watts? We have 70 watts laser, but the laser is not going to give that 70 watts. If full potential of laser we are using means it easily get reduced its life. If the normal laser power is 10 years, normally it not come 10 years, 3 to 4 years, but we using 70 watts completely, it will give 2 to 3 years only it will come. Maximum of 2 to 3 years. If we use that much, it will get below that also. So in machine setup itself they allow us to use maximum of 40 watts. Okay. Also we need to do this kind of research. We need to change the parameters. We need to get license called as parameter editor. That license also we need to get. In PDC we don't have that license. In academic research persons only they will get that kind of license. It also costs around 10 lakhs. Why? Because I am telling means we can't easily get this kind of research facilities in our outside. So I run around many IITs, NITs to get this kind of research, but there is no places for me. Then only we build by our machine with the project UP with the help of UP UGC. Then only we done this research work. Okay, come to the point. This is the laser power. How much laser, what of laser, whether it is a 30, 39, 40, 41, which thing we can use. That is a page come here. Next one is that distance. Distance is nothing but the one layer of if okay, just think this is the first hatching. The laser move on the particular line. This is the first line. This is the second line. Then how the first and second line overlap. So that is the overlapping. To control that overlapping, we need to finalize the hatching between the distance between the each hatching. That means not layer, one movement. Sir.
Okay.
Top you have see top view now. This is the first. It is the cross section. This is my product cross section means laser will move like this, complete. So for each line there will be overlap. Overlap should be there. Otherwise, what happen I will tell you. If laser power is more reduced, energy, I tell you the point of energy density. Energy density is low. There will be a unsintering portion will be there. So pores will be there. So it will affect the density and property of the lattices. If overlap is more, then there will be a over sintering. So part get brittleness get more. So it will easily deform before absorb more energy. So we need to consider that overlap, that means hatching distance. Then third thing is speed of the laser, how fast it will go. So these are main three parameters. Last one is volumetric thing, that is the layer thickness come here. So these are overall parameters, but you go with the fabrication of lattices with the parameter editor now, you can't change the layer thickness, particularly polymer machines. So you can consider these three things and change the energy density, but this energy density range also should be in the range for particular material. For example, PA12 energy density will be 9.5 now. You can 9.5 to 10.5 now. You can play with in between this range only. You can't go above or below. It will directly affect your powder. If you go with above 10.5 now, your bed will get fire. It will get fire. We done that one also get fire. So we have to stop the powder build. We take the powder. Why I am telling is cost of the powder, especially buying from EOS or German based, it is high. 1 kg of powder cost around 10,000 rupees. For this one component I have to print with build now, it is 2.5 centimeter height. I have to put 5 kilo of powder. Here 2.5, here 2.5 minimum. So for single build I have to put 50,000 worth of powder. So we need to more conscious on this when we go for fabrication. That is not that much rocket science. By practice we can, it will come sir. So I take these three properties as a thing, and I added relative density for that. Then I fabricate, I do Taguchi analysis, DOE. I fabricate the part and test it with compression test, UTM. Then I get stress strain curve, which I shown there. First portion is linear elastic region, second one is plateau region. Since it is a bending dominated structure, I get only smooth plateau region. So the energy absorption will be good there. So densification, particularly in densification, what properties we get means we get material property of BH1 or which material fabricated with the lattice structure. Why means there in densification all the voids are get closed and it made as a solid component. After that you compress now, it will act as a solid structure. In that I make a SN graph and found what is the best parameter for particularly this kind of structure. So it is an initial research. This is my PhD work. For my PhD work, I selected 5 different unit cells, which have different topologies. In that, 3 are bending dominated structures, 2 are stretch dominated structures. So I fabricated with 10, 20 and 30 relative density and tested. I will show you. These are the 5 different unit cells I selected for my research. Then 3 levels I take. Why? Because I take another one parameter as strain rate. Why? Because there is a governing factor for lattice structure. First one is relative density, then unit cell type, then what material we going to use. Fourth one is what load going to act on that. How far, that means quasi-static or impact condition. Based on that, the property of lattice structures will get increase or decrease. So we have to finalize or we have to learn how which relative density is best for my application. So what I done, I select 10, 20 and 30 lattice structures, relative density, and for my all 5 lattices, for all these 5 unit cells I fabricated, designed my lattices and fabricated. Okay, with this Taguchi analysis. Then each and everything I compressed with different unit cells. Around 150 lattices I fabricated and printed, print and tested. What I get is, whenever I am compressed with Kelvin, 300 oxatic and simple cubic unit cells. I show you 5 unit cells, right? This is a simple cubic, that is Kelvin, that is 300 oxatic. This is OT, that means architect stretch laminated. This is FBCCXYZ, that is nothing but face, body and center, centroid XYZ lattices. Okay. So each and everything I tested with compression test with 3 different compression speed, 2 mm per minute, 20 mm per minute, 200 mm per minute. So I take below value, higher value, mid value to get how the property is getting changed. So analysis, I get only one or two lattice structures show different properties. Other things are based on the relative density and strain rate, it gives same properties. Only 2 things get different shown different properties. These 2 things, simple cubic and redundant, deformed as same manner. What is nothing but bending here happened, but before bending it because of vertical orientation struts and horizontal, even though it is bending dominated structure, it deformed as a structure dominated. But you can see it will came out of the boundary, right? Like this kind of deformation we observed. First it showed progressive failure. First this layer of unit cell get deformed, then another layer, another layer. Like kind of progressive failure I get. So it will impact on my stress strain curve. So you can see the fluctuation in the plateau region. Okay. This is the reason for stress fluctuation, what I already explained. Then this is a Kelvin based lattices. It is a bending dominated structure. For 10 and 20% I have shear band failure. That means applied load transferred to this incline and deformed as a bending dominated behavior. So I get more plateau regions, smooth plateau region. It will suitable for energy absorption application. Simple cubic REI structures suitable for higher stiffness, have a higher stiffness, so it will be suitable for more strength purposes applications. So, but I also observed that for 30%, when density get increased compared to 10 and 20, it deformed as a progressive failure, and also the same thing expected on the graph, and we get fluctual deformation. So next structure is arctic stress, where the deformation is progressive by the same as, and we can get graph also like fluctuation thing. Okay. Okay. Here we observe two kind of deformation. First one is the studs. There is a stress pinpoint happen. What happened now? When compressed, the studs get deformed as a this kind of bending happen here, and after that only full compression happen. For the 10%, 20% this pinch happen on the node area due to the higher dimension, higher radiative density. So this kind of two things we observed. It will play on the overall deformation of the lattices. So this kind of deformation we get based on the increase of relative density also. So next one is final structure is FBCCXYZ, which is based on the maximum stability criteria. It is categorized under overstrip structures because its M value is higher 0. So it's, I think it comes under 5, I think M value. But while deformation and mechanical properties, it show minimum properties compared to simple cubic structure. Why? Because the structure will have number of studs in its topology. Vertical studs also, inclined studs also. While compression, what happen is the inclined studs compressed as a pre-deformation manner. When it absorbs the energy, it not let vertical studs to absorb more energy. It will drag vertical stud to get buckled easier with minimum load. So we get minimum compression strength and energy absorption compared to other structures. So with this research study, what I conclude that maximum stability criterion is important to categorize the lattice structures or unit cell, but that is, modern designs, it is not fully suitable. So we need to study the topology of the lattices with respect to the loading condition. If your stud is vertical to in the parallel direction of the loading direction, so it will deform as a buckling, so it will absorb more energy. Whenever bending happens, it will absorb minimum energy of initially absorb minimum load and get bent. So these are the observation we have observed. Then this is a comparison. All the structures shows compared to 10 and 20%, 30% get more energy absorption. Then I done vibration damping testing also for same structures, and I formulated FR, that is frequency response function, which is called. In that I calculated frequency value and damping ratio value. This is the response of frequency response. In that I observed that Kelvin structures which are have vertical and stiff structures show more natural frequency and lesser damping ratio. The structures have bending dominated behavior, which is suitable for energy absorption, have lesser frequency and more vibration damping characters. Also, when we go with okay, fine. Actually, when to compare the natural frequency or damping ratio with relative density, 10-20%. When relative density getting increased, the natural frequency get decreased. Actually, but what is the value equation for natural frequency is omega equal to root of k by m. What is the means? M mass getting increased, the natural frequency should get decreased. But what is happening here? Whenever relative density mass getting increased, frequency also getting increased. Why? Because the stiffness factor k plays a major role here. Compared to mass, stiffness factor make more impact, so it will increase the natural frequency of the structures. These are also one of the inference we got to this research. So comparison, with this I selected 3 structures. before going to the next one, I want to tell thin wall tube is another one important feature for energy absorption. It is one of the component which is widely used for many aerospace, automobile, other applications. It will during the impact or collision, it first of all it observe the load and deform, then only it will give load to other parts or passengers inside the car or anything. So our objective to incorporate the lattices is it should get observed and deform. It should not deform, and if the structure not deformed, it will directly displace from its position, and it also impact on the inside the other parts and inside the passenger of the car. So our motive is of latticing our component is it should absorb energy and it should get deformed first of all. Then only it will transfer the energy. So obviously when it get absorb the energy and deform, it will reduce the impact load. So get the other parts and passengers will get minimum impact. So this is the main motto. We using lattices for the cross-worthiness application. So these are the widely used components for the thin wall tubes. In this work, then continue my research work. What I done is I incorporated my lattices to this thin wall tubes. Why? Because the thin wall tubes were already I shown the figure. It is have plenty of application throughout the industries. So what I done is I take one bitubular structures. Actually, in the current research, in the current industry, have lattice filling approach for the same structures. They done many work, but particularly for single tube. They done only for this tube, latticing approach. For this tube, they not utilize. But what is the research telling that when you go with two bitubular structures, it give more efficient compared to single tube. So what I done, I take two bitubular structures and incorporate different lattices to the here. From the result, I take three structures and incorporated. For study purposes, initial test I take only single tube and fill all the three structures and test it. For second one, take bitubular structure and fill different kind of units inside and outside. Different things I done and tested. This is a cross section, and you can see the top view. These are the lattice infilling I done with my work. This work already available in published in the cellular plastic journal. You can refer this one also. So I fabricate all the thing and tested with the compression test with two different speed. One is quasi-static, another one is high impact test, medium impact test I done. And these are the equations we need to consider for cross-worthiness application. First one is energy absorption, second one is mean thrust force, third one is thrust force efficiency. All the three things we need to calculate during the cross-worthiness application, even though for bumper or any other cross-worthiness study. So this is a deformation behavior I observed. What I observed is all the structures give progressive failure. But when I compressed these two structures, CK and CO, what it means that CK means outer shell have simple cubic lattice, inner shell have Kelvin lattice. Like this I formulated these designs. When I compress all the designs, all are showing progressive failure. Like this, each and every layer get progressive failure. But when I compress these two, the outer cube structures get stretched outside, so that global buckling was happened. So during the compression, in between, my sample came out and the deformation compression test was stopped in between. So I finally conclude that these structures are not suitable for energy absorption application. Why? Because it get stretch dominated behavior, so it will not absorb that much energy. So in this work I complete this one. These are the data. Then next one is negative stiffness. I hope all of you know the stiffness, right? Negative stiffness is nothing but when the structure gets deformed, it will go for elastic region to plastic region also it will compress. When we remove that load, it will regain its original position. That is called negative stiffness property. That property is mainly because of that structure, not material property or loading condition. It is only purely for structure of the unit cell. You can see here this portion, right? This curved portion. When you give the load, the curved portion get compressed. When you release that one, it will come out its original position. Okay. This is the main property of this one. And then also we have we done in this structure we done functional grading. You can see the thickness of the horizontal stud getting changed. Here the vertical thing getting changed because these two only getting more influence on the property of this structure. The curved portion give the negative behavior, but how much strength it should observe, that one controlled by these two parameters, two designs. So I changed that one and tested with compression and also impact test. Then in FEA, what we done, we incorporate this design to this bumper design and tested and we done with hypermesh software. This is done by my student Mr. Harigan. He done this work.
And actually, what is the material?
For this PA11 materials.
PA11.
PA11, polyamide 11 material. It is also kind of.
Most probably it is a ductile property.
Actually, it is a ductile property. We have ductile in nature. We can also use PA12 material also for this. Actually, this design, other people also done with the PA12 material. They also get this property. Why we go with PA11 means to enhance more negative stiffness. So we done with PA11. If we go with a glass filled polyamide, we directly get break. But it absorb more energy. But after that it get break. It won't come its original position. That is the motto of this material we use. Next thing, same application, same property only, but we choose different structures and then FEA first. You can see how it will get energy and compress. Then after leaving, how it will regain its original position. This is the structure. Then we will fabricate with the same material PA11 and tested FEA and compression test. Then we finalize particular design. Actually, we done two different designs. Then finalize one design with the relative density. We incorporate that one with the FEA for electrical vehicle. Actually, nowadays electrical vehicle get more market rate. But one of the issue from the starting itself, what happened is due to the impact of any stone or anything in the road, the battery get impact and get fired. Already 2 to 3 cases in foreign and India was recorded due to this thing. While running the bike or car, the stone from the tire, the tire get compressed the door, anything stone in the road, it will impact on the battery cover. So easy that impact blast the battery. Due to that, 2 to 3 accident already happened. You can search in net also. So to rectify that, we incorporate this lattice structure in this particular below the battery cover. So if any impact on that, that impact can be absorbed from this lattice and it will absorb in the lattice and it will not transfer to the battery case. So it will reduce the accident scenario. That is the main motto. Then this is my ME work. Actually, it is a hybrid work. What I done is, we know ECM, like electrochemical machining process. In manufacturing department CG, we have ECM machine. The purpose of that machine is by conduct in the electrolyte by use of electrical energy to remove the particular shape on the workpiece. This is a motor. But when we use continuously, the particular part which is tool holder, which is made up of stainless steel, get curved. So each and every after particular year, we need to each and every experiment we need to clean that one with acetone. In my ME work, I plan to change that one to replace that one with the additive manufacturing. What I done is I fabricate that one with the ABS. I do reverse engineering here with a simply vernier caliper. I measure all the data and design the samples and fabricate that one. But what is the main problem I face here is conductivity. Because tool holder main job is two. One is hold the tool and move in the with that bed. Next one is it should conduct the electricity from the machine to tool. When I change the design and when I fix with that, I can easily hold the tool and movement also I achieve. But what happened? I face conductivity problem. So what I done is I done electroplating on my ABS. It is a ABS material. I done electroplating on the ABS material. Initially I can't do it. I can't done that one. So what I do is first of all I done electroplating, electrolysis plating. First I done electroplating. So it will remove the butadiene layer on the surface of the ABS material, that component. Then I deposit nickel on the initial layer minimum thickness. Then I done electroplating on that to increase the thickness of the nickel coating. Then I use that one with machine and fabricate that one. When also I face one problem that it is a collet which one directly hold the tool holder. It have a minimum thickness. What happened that during the coating it get break. So what I happened done I redesigned that one. Same time it should hold the tool also when I tied with the tool. At the same time it should not break. So like that I done 3 to 4 iteration and finally came up this design and done work. Also another one objective of my this work is to redesign this tool holder. Why? Because it have 3 components, not an issue. But when I tied with the tool, if the tool diameter is 0.3 mm or 0.4 mm, it get break or it get deformation. What I plan to redesign that one. So I incorporate part consolidation theory here and change the 3 component into 2 component. In that also I electroplate on the one thing only. Actually, the name of this thing is shank, collet, holder. These are the name of this one. What I done is I merge the design of collet and shank as a single unit there. That is the top portion. Next one is only holder. To what is the use of that holder is when I push that holder shank to the holder, it will tight the top portion of the collet. So it will easily hold that tool. So like that I fabricate, design and fabricate that one. The GIF image you can see this one I have to place all the 3 components and type. But here only 2 components and assembly time also minimum. Then I fabricate and tested with as usual procedure. I followed ECM machining and found that compared to stainless steel, I got more efficiency and minimum voltage drop for my nickel coated tool holder. This work also published. If needed, I will. Then this is the final work. In this work, what I have done, this is the same thing. This is a tool workpiece holder for ECM, electrochemical micro machining. In that, what happened na, our senior researchers who are doing and done the work in ECM, they fabricate tool workpiece with ABS or PLA material with additive manufacturing. They put glue on that and make the magnet on that and place the workpiece to hold the workpiece in the electrolyte bar. what happen is that it get the magnet get day by day magnet get efficiency loss, also it get getting color change. So what we done, me and my senior Prithvi Rajan, you saw yesterday, right? He and me have done this work. What we done is we change the design with the help of cantilever beam condition. We designed that one and fabricated with a 3 iteration. We found that best design. Here we reduce the use of glue and magnet, just pushing the two portion outside portion of the thing. We push it and insert the workpiece and place on the ECM and done the fabrication process. Sorry, ECM machining process. Okay, these are the works we done. If any doubt in this, please ask.
Relative density 10%, 20%.
Yes, sir.
How you were selected with reference?
So actually, Gibson quoted that above 30%, the structures place as a solid structure with minimum force like that. It will. What is the meaning of that? Meaning of that, above 30 degree, the material property will be more, structural property less. So with that, I take 10, 20, 30%. And that also for each structure, there is an equation for that to calculate the relative density. So for each structure, what I done, I fixed the length of the stud. I changed the cross section of the diameter of the stud and come with the.
Can you show me the table for this? Before.
Yeah.
Last class. Last.
Yes.
Last. First. Hatching distance also I can understand. What is that, sir?
Yeah. Hatching distance is nothing but if I have my cross section, SLS 3D printing I am going, the cross section is this one. What happened? My laser will sinter line by line. Okay? The previous line, then next line.
It will go like zigzag like this or
Sir, it is programmable, sir. It will go different different manner. One layer will put as X direction, next to Y, then X and Y, both things will happen.
so the hatching distance is that this distance
For
between
particular layer, this is the first line, it is the second line. The first and second line merging one particular area overlap. That is the overlap is a
0.2.
this is the overlap area. Hatching distance is the mid portion and another line mid portion gap between that one is hatching distance. This is the single centering line, sir. This is a single centering line. The centering is the cross section of circle. Okay, the mid portion and mid line. The distance between these two is a hatching distance. Okay, if you reduce the hatching distance means both layers get more wedge. So over centering will be happen there. So it will easily break. If you make more distance now, the wedging is minimum. So holes will be there, pores will be there. So it will affect the density and properties also. Any other doubts?
Any queries? Okay, thank you, sir. The wonderful presentation. We gain knowledge about the presentation and your work also. You did a lot of work, sir.
Thank you.
Okay, thank you once again. Thank you, participants. We have the article summary session. Already I shared 4 articles, 4 journal in the WhatsApp group. You write any, take any journal and write the articles. Either soft copy or handwritten copy. சார் பண்ணுங்க, நான் லிங்க் கொடுக்குறேன். நைட்டு ஈவினிங் கூட பண்ணி அனுப்புகிறேன். கண்டிப்பாக வேணும் சார் டாக்குமெண்ட் போர்ஷன். இது ஆர்டிக்கல் சம்மரி. நம்ம டெய்லி டிஸ்கஷன் இருக்க ஒரு செஷன் வந்து நம்ம இது இருக்கு இல்லைங்களா ஜர்னலில், நான் 4மே அனுப்பியிருக்கேன். நீங்கள் ஜஸ்ட்டு கூகுள் பண்ணி ஜாட்சிப்பில் கூட நைட் போட்டு ஏதாவது ஒன்று போடுங்க. நான் சொல்ல டாக்குமெண்ட் பர்சன்ட் வேறு ஒன்றும் கிடையாது. அதே மாதிரி இது இருக்குது இல்லைங்களா, இன்னொன்று போட்டிருக்கோமே ரிஃப்ளெக்ஷன் ஜாட்டான்னு சொல்லிட்டு, அது ஒரு ஃபார்மெட் அனுப்பியிருக்கேன். அதையும் பண்ணுங்கள். நான் லிங்க் கொடுக்குறேன். ஈவினிங்குள்ளே போடாது போட்டிங்கன்னா நான் ப்ராசஸ் பண்ண முடியும். அது பண்ணால் தான் ஃபீட்பேக் லிங்க்கே அடலில் வரும். நான் ஒரு மாடல் ஒன்று அனுப்புகிறேன். ஒருத்தர் அனுப்பியிருக்காரு, அந்த மாடல் அனுப்புகிறேன். அதே மாதிரி கூட பண்ணிடுறேன். கேண்டிடேட்டை விட நீங்கள் வீட்டில் கூட பண்ணிவிட்டு எனக்கு லிங்க்கில் போட்டுருங்க. அது போட்டு ஆமாம்.